Kids, welcome back to Mr. Murray's Math Land. And hey, if you're loving derivatives, and I know you are, then you're going to really love today because we do the second derivative and the third derivative and the fourth derivative, etc., what are called higher order derivatives. But they're not really that big a deal. If you understand how to take a derivative, then you know how to get a second derivative because it's just the derivative of the derivative. And you go on as far as you need to. So just as you know, notation is very important in this class going forward in calculus. And so if a function is called f of x and we call the first derivative, the derivative, we just call it f prime of x, right? That indicates the derivative. If you take the derivative of that, you get the second derivative, and notice how it is represented. That is denoted with f double prime, two apostrophes. So the second derivative, or f double prime. And if you go beyond that, if you were to do the third derivative, the derivative of that, then you might see 3 apostrophes. But if you start talking about the fourth, fifth, sixth derivative, etc., you're not going to see like 6 apostrophes because nobody wants to be counting these. They want to just be able to tell quickly what kind of function you're dealing with. So they'll usually just put the number there. If you were doing the 6th derivative, they would just put a 6 there. And from context, you would know that that means you're not raising it to the 6th power. It means the 6th derivative. So that's the classic function notation. Notice the Leibniz notation. Obviously, if it's y, you could call it y prime and y double prime, and then same idea, y nth, derivative. But if you're in the Leibniz notation of dy dx, remember that's basically standing for slope, minuscule change in y over minuscule change in x. And if you take the derivative of that, notice you get d squared y over dx squared. And that's really representing, if you take the derivative of this, but with respect to x again, what you get is the second derivative, and that's why the top of the d is squared as it looks, the second derivative of y, the original function. And the denominator is saying with respect to x both times. And if you go to the third derivative, fourth derivative, and so on, you'll see that number there. But again, I don't expect you to have a full understanding of that notation just yet. But it's good to try to ease yourself into it. Now, the actual problems, very easy. If you want you've got f of x equals this polynomial, and they say find the second derivative, you don't jump right there. You get the first derivative first. So let's get the first derivative. F prime of x is, classic power rule, 21 x to the 6th minus 40 x to the 3rd plus 18 x squared plus 5. 2 is the constant, it drops out. And now the second derivative, what I'm really after here, just do the derivative on that. So 21x to the 6th, that's going to be 126x to the 5th minus 120x squared plus 36x. And now 5 is the constant and drops out. And there we go. Pretty simple if you're in the power rule format, and even if it's radicals or a fraction and you rewrite it to use the power rule, you would just keep going, and same deal, no negative exponents in your final answer there. Very simple. Good to see one of these, though. Number 2, find the second derivative of this function. And notice this function is the product. That's 5e to the x times cosine of x, so that requires the product rule to get that first derivative. So, be careful here, organize, or if you're doing it mentally, just don't make a silly mistake. A is 5e to the x, a prime is 5e to the x. B is cosine of x, b prime is negative sine of x. And so our first derivative, and I don't really care if you call it y prime, even if they choose to use this notation, they're synonymous, so feel free. But I'm going to go out of my way and say, hey, that's dy dx is product of the inners, 5e to the x cosine of x, plus product of the outers. And since this is plus, this becomes a negative there, so we get minus 5e to the x sine of x. There's the first derivative. And now I've got to take the derivative of that to get the second derivative. And you may have seen this coming. Just to do the derivative of this portion is going to require its own product rule. And then to do the derivative of this is going to require its own product rule. So really, two more product rules to get this. So you can see it can increase in difficulty the further you go with these, depending on how complicated it gets. So same deal. Now, if you do want to take a little shortcut, if you can handle it, the second derivative is to do the derivative of this. Notice you just did that. It's the same function you started with, and that gave you this. So doing the derivative of this should just give you this rule that's already set up over here on the side. So by all means, do it again if you want. Rewrite it out, do the whole thing. But sometimes you don't even notice that sort of thing till you're done. But hey, I'm just going to save a little time. It's the same thing. Oh, cool. So just doing that gave you these two terms. But now you've got to do the derivative of that, and that we have not done. So I'll do a little product rule off to the side here. And again, if it starts with a negative, just, you either got to distribute that negative to the rule or include it with your, first function in the product rule. So a is negative 5 e to the x. A prime is negative 5 e to the x. Got to love that e to the x rule. B is sine of x. B prime is cosine of x, right? Positive cosine. And so your derivative of that's going to be the product of the inners, which will give you negative 5 e to the x sine of x, plus the product of the outers, and that will be plus a negative, so minus 5 e to the x cosine of x. And you could leave that, but if you'll notice, there are some like terms, so it's kind of nice to clean that up a little bit. 5 e to the x cosine of x minus 5 e to the x cosine of x. Cool. Cancel each other out. And these, minus 5 give you negative 10 e to the x sine of x. Yeah, particularly with e to the x's and with trig, you get a lot of like cyclical kind of derivatives the deeper you go. In fact, at this point, I'm going to offer you a bonus problem. If you want, you have to write up your solution and send it to me. Show me your work, show me your explanation, and here's the question. What is the 50th, yes, 50, the 50th derivative of sine of x? 50th derivative of sine of x. Worth a bonus point if you like. Nothing big. But okay, now the big thing here is you'll do a lot with this next year, but it's good. You might be curious, like, what does this even represent? The first derivative, we got that. That represents the slope of the tangent line, or in other words, the slope of the curve itself at a given point, the instantaneous rate of change. Or if you're in physics, that first derivative represents the velocity if you're taking the derivative of a position function. Well, the second derivative would be the derivative of velocity, or the rate of change of velocity, and that would be acceleration. And here's a couple of graphs to maybe help you visualize that too, to tie it together. That I just use stocks, for example. Here's a stock and its value over time, and here's a stock and its value over time. They started at the same value and they ended at the same value, but they didn't behave the same way to get there. This one is definitely, it increased in value, and so did this one. But how did they increase? So let's take a look at their f prime values. F prime would be the slope of the tangent line. So let's look at some little tangent lines in here. If I were to pick some spots and draw some tangent lines, notice they always have a positive slope because the graph is increasing. But look at what's happening to them. They are positive, but they are flattening out. The slopes themselves are decreasing, even though the function is increasing. And that's kind of what, with all this pandemic stuff, we're talking about, like flattening the curve, like that rate of change, decreasing it. There's the rate of change, still going up, but going up at smaller values each time, a smaller slope each time. And here, yes, same deal. Anywhere I draw a tangent line, it has a positive slope. The graph is increasing, but notice those positive slopes are bigger and bigger as you go along, right? This is bad. This is like exponential growth. So this is if this is f prime and this is f prime, f double prime represents the rate of change of this. So f prime, the slope is positive. F prime, the slope is positive. But the rate of change of that slope, in this case, f double prime is positive because the slopes themselves are increasing. In other words, f prime is increasing or has a positive rate of change. But in this case, the slopes are decreasing even though they're positive. So we would say the second derivative is negative. And that's like your acceleration idea. This would be like you still going forward as you approach a stoplight. Your velocity is still positive, but you're slowing down. Maybe if you're pressing the brake, your acceleration is negative even though your velocity is positive. And this might be like you're accelerating, you're pressing on the gas. Hey, you're going forward and you're going forward at a faster and faster rate. Your acceleration is positive. So the characteristic of these two graphs is what we call concavity. This graph, this region, when you have this sort of thing, that is called a concave down region. A concave down region, one in which the second derivative is negative, and one in which the second derivative or the acceleration is positive, is called concave up. I'm talking about the concavity. And it's easy to just visualize, say, an upwards parabola is the most classic concave up, and a downward parabola is the most obvious concave down graph. And you see, this looks like it could be a portion of a downward parabola, like a piece of a downward parabola. And that's how you can visually tell if the second derivative is positive or negative. Does it look like it's a portion of a downward parabola, or does it look like it's a portion of an upwards parabola? And it's concave up and its derivative would be positive. So in words, I know we're throwing a lot of ideas here at you, and I don't expect you to master them all by tomorrow or anything, but it's time to start thinking about these things. What does it mean when you learn this? Anybody can take that second derivative, but here's how we would describe this. This graph was increasing at a decreasing, so that really should just be at a decreasing rate. Increasing at a decreasing rate. Increasing, first derivative positive. The rate of it, though, decreasing, second derivative negative. This graph was also increasing, but and that one should be n, at an increasing rate. Right? First derivative positive, and the rate of change of that is also positive. Second derivative positive. Okay, so here's a graph, and I'm actually giving you the equation so you can find these things and verify it algebraically. But ideally, you would be able to look at these various points on this graph and tell whether the first derivative at -7 is positive or negative. At -7, that same point, is the second derivative positive or negative, or equal to 0 potentially. -1, same deal. So let's just take a look here. Here is the function, this nice cubic function. First derivative f prime of x is 3x squared plus 12x minus 15. Part B, when does f prime of x equal 0? That will be when the slope is 0, and hopefully you can actually see that on the graph, but let's solve it algebraically. And so when I set this equal to 0, I'll take out that 3x squared plus 4x minus 5. I can further factor that to x plus 5, x minus 1, and that means it equals 0 at x equals -5 and +1. And hopefully that makes sense visually anyway, because at -5, we've got a horizontal tangent line, a slope. It's that maximum point on the graph. And at 1, it's the other place where it's got a horizontal tangent line or a slope of 0. Now, find the second derivative. Second derivative, so take this equation right here and do its derivative. The second derivative of 3x squared plus 12x minus 15 is 6x plus 12, and the constant of negative 15 drops out. Well, where does this equal 0? This is a linear equation, should be pretty easy to solve. Just subtract 12, divide by 6, x is negative 2. So what significance does this point have when the second derivative is 0 at negative 2? So let's take a look. That would be right here. And if you can make that connection that we looked at here, if the second derivative is negative, you're concave down. If your second derivative is positive, you're concave up. If your second derivative is 0, like at this one single point, then it has no concavity at that point. And what's happening is the concavity is actually changing at that point. This is where it's switching from concave down. You see how it kind of looks like a downward parabola on the left side of that point. But then at a certain point, the graph switches and it becomes, hey, concave up. It's like a piece, like an upwards parabola. And that is the exact point where it happens. So you can test these things, of course. So f prime of negative 7, f prime of negative 7, we're right here on the graph. F prime, if you're talking about f prime, you're talking about the slope. That is definitely a positive slope. So f prime f7, negative 7 is greater than 0. You don't believe it? Plug in negative 7 into this f prime and you'll get a positive number. Trust me. Or do it. Don't trust me. The second derivative at negative 7, that's new. You might not quite trust it. At this very point, is the second derivative positive or negative? Why not just plug it in to be safe? If you plug in negative 7 in here, you get negative 42 plus 12. That's negative 30. You get a negative value. How should you have known that it's really going to be negative? Because this entire region here, before that point, that entire region is concave down. CC down, I abbreviated. And that entire region, if you plug in any x value to the left of negative 2, you're going to get a negative quantity, and that's what this is visually showing you. If I go anywhere to the right, any x value to the right, you're concave up, and your second derivative is positive. But, so here's another one to check that out. At negative 1, f prime of negative 1. So negative 1 is right here on the graph. F prime refers to the slope. You know, the first derivative refers to the function itself is decreasing. We're going down. It's got a negative slope. Don't believe it? Plug in negative 1 into that first derivative. It's definitely negative. The second derivative, however, you're right here. You're part of this concave up region. Your second derivative at negative 1 should be a positive quantity. And you can check here to kind of convince yourself since it's the first day. But if you plug in negative 1, 6 times negative 1 is negative 6 plus 12. That's positive 6. And one more way to maybe think of it all is that throughout this whole concave down region, if you were to look at all the little tangent lines, or at least a series of them, sometimes the slopes are positive and sometimes they are negative. But throughout the whole concave down region, the slopes are decreasing. They're positive, but they're getting less positive, less positive. They're 0 at the top, and then they're negative, and then, you know, more negative if you want to say it that way, but that is smaller and smaller, and that's what's happening. It's a negative rate of change on those slopes until you get to this point right here where it changes, and that is sort of the most negative it's gonna be. After that point is when it starts to turn again, and now it's still negative, but it starts to increase. You know, if that was like, say, negative 5, a slope of negative 5, well, this is going to be maybe something like negative 4, negative 3, 0, and then positive, positive. So throughout this whole region, the slopes might be negative, 0, positive, but the slopes themselves are increasing. It's a positive rate of change of the first derivative. And that's what the second derivative is measuring, the rate of change of the first derivative. So hopefully that made a little sense there. I know I kind of went on at length, but if you're watching this on double speed, maybe you watched it, maybe kicked it up to quadruple speed for this one and made it tolerable. Or maybe you just shut it off, who knows. A couple of final points here. The spot where this changes concavity, it has a name. They call that a point of inflection or an inflection point. And if you think about the word like inflection in your voice, like changing how something is sort of growing, and points of inflection, that was all over the news when they were talking about this pandemic. We're trying to change the inflection of this graph, waiting for that inflection point to occur where the rate of change of it would start to shift. So here's just the last second thing if you want to try and see if you can get this. I'm asking you on a graph that looks like this, I just drew a little crazy polynomial. How many changes in concavity does this have? AKA, how many points of inflection? Can you visually tell anytime it switches from concave up to concave down or vice versa? That's a point of inflection. So can you see how many it has? So if you'd like, hit pause for a second and try and just see if you can figure it out just for fun. And okay, maybe now it's unpaused and let's talk about it. So here's the deal. Let's just trace along here. And we are definitely part of a concave down region. If you look at that, that looks like part of a downward parabola. Downward parabola, downward parabola. Sounds like a yoga pose. But at a certain point here, it starts to look like an upward parabola. So I don't know exactly where, but I know somewhere right around there it switched to being concave up. So there's one point of inflection. And we're certainly not done. But we keep looking, and then look, there's another downward looking parabola. So again, it shifts somewhere from here to there. It switches again. And I'll just put a dot right around there, it looks like. And so we're concave down, concave down, concave down. But notice what happens here. Now you got this weird little part in the graph. If I were to cover up everything else, and if I had said, hey, that is part of a parabola, is that an upward or a downward parabola? Because of that curvature, I think everybody would say that's part of an upward parabola. And that's because we switched concavity again. We are back to being concave up here. So another switch, so we're up to 3. Concave up, and then, hey, look at that, that's concave down again. Look at, it's just a piece of it. It's not a full, it's not easier to see it when it's like this. A little harder to tell, but you really look, that's concave down. Look at that. So we switch again. Now we're back to being concave down, up. Somebody switched to concave up again here. So we got another one there, another one here. Concave up, concave up, concave up. It switched again right there, that little section right there. It looks concave down, up, and then it switched again one last time to being concave up. So 1, 2, 3, 4, 5, 6, 7. That had 7 inflection points on that graph, or 7 changes in concavity. So okay, hopefully we tied together some ideas about what the second derivative represents with regards to the first derivative and with regards to the original graph. It represents concavity, and getting the derivative itself isn't that big a deal. You're just using the same rules, but it's nice to have a broader understanding of this, what it represents. So ask me if you got any questions or if anything was unclear here. That would be totally normal being the first day. So have a good day, good luck, and ask if you got any questions.